This is our traveling combustion chamber, and as you can see, it consists of two halves. And the first thing we have to do is to fit these nuts into these holes. Next, we're going to take two little springs and we are going to place them inside these slots. And then we are going to bolt everything together. And as you can see, we have just made a little happy face. And no happy face is truly happy without some hair and a little hat. And there we have it, one complete traveling combustion chamber. And here's one I made before, because we are going to need two of them. As you can see here, our traveling chamber has a slot. And that slot fits into another slot into our rotor. So we take this, we take the other chamber, goes in the other slot. We have a little spacer, because I print first and think second. And then we have the other half of the rotor. And now we have a rotating assembly. Next, we're going to take this back plate and then we're going to press this bearing in here. And then we're going to bolt our back plate to our housing. And then we're going to install our rotating assembly. Together with these 4 little seals. And voila! The traveling combustion chamber oval rotary engine 2.0, leaner and meaner than ever. Now, I promise that later in the video I will explain why this one is called the oval rotary engine as opposed to its predecessor, which was called the elliptical rotary engine. But right now what I want to tell you first is what makes this thing so much better than said predecessor. First up is the anatomy. As you can see, this engine actually rotates without much resistance, unlike my previous design. For the previous design, I cut my seals by hand, like a caveman, and that's because I didn't know something that apparently most of my comments section did, and that's that you can 3D print TPU, aka thermoplastic polyurethane, aka stretchy rubbery stuff with a high temperature resistance that's great for seals. Here's some TPU filament. Look at that, look how stretchy that is, look. And that's why all the seals on this engine have been 3D printed using my Bambulab H2D 3D printer. In fact, the entire engine, save for the little springs inside the traveling chambers, has been 3D printed. But this time around, I didn't use basic filaments for the body of the engine. Instead, I used the most badass filament Bambulab has to offer. pps-cf. That's polyphenylene sulfide. Yeah, I got it right. Polyphenylene sulfide combined with carbon fibers. Now, PPS is in itself already an engineering plastic, meaning that it has a very high temperature resistance. It's resistant to chemicals, to solvents, you name it. And then when you combine it with carbon fibers, you get a 3D printing filament that's an absolute powerhouse in pretty much every aspect you can think of. Here's a little something I printed for demonstration purposes. Finally. And as you can see, this wasn't even a solid part. It's only 25% infill, which means that 75% of this is just hollow. All of this means that my engine won't melt and or fall apart like it did last time. The only downside of this filament is that it's very brittle. So this engine, in fact, has been made from the most rigid and the most stretchy filaments out there, which I think is kind of cool. Now, I could keep talking about this, or I could set it up and try to start it. So here it is, set up, fully set up, probably the most homebrew thing you'll ever see. Now, this is how it works. For the spark, we have a little 12-volt battery. We have the positive going right into our high voltage generator, basically a little spark generator. You can get these on Amazon. They're super cheap, kind of dangerous, but as I have just learned, they're also really unreliable. This is my last one. 2, I have them here. 2 have already failed on me. This one did 2 sparks and then just died. I just tested this one and it works, and I'm afraid to test it anymore. I just want to try the engine while this thing still produces a spark. Now, the negative side of the spark generator goes here, and then to this wire, and then to this wire, and then on the shaft of the rotor, here we have a copper wire. So as the rotor spins, this copper wire touches these 2 wires and closes the circuit and creates a spark. Now, I had a switch here, so I can kill the whole electrical system immediately if something goes wrong, which it will. But I thought the switch was bad, so I tested it. It's not. It is definitely these things that are dying on me, my last one. I really hope it works, because if it doesn't, then I have to order another one and wait, and I cannot wait anymore. I've been at this for a full month and I just want to try it. Now, for the fuel, here we're going to hook up a clear tube that's going to go to this, which is a part of this, which, as you can see, is a propane butane canister. We have 30% propane and 70% butane. I know this looks really dangerous, and this whole thing, the more I look at it, the more it looks like a homemade bomb, but I promise you it's not a bomb. This is an actual engine. This is not as dangerous as it seems, but obviously do not try any of this at home unless you really know what you're doing. This is good. I'm using this because this eliminates any issues with the carburetor. So, is atomizing fuel properly, too much fuel, too little fuel, running too rich, floods the spark, whatever. This eliminates all of that. It's already vaporized, a mixture of vaporized fuel, so it makes starting hopefully easier. If it can run with this, it can run with anything. Okay, this is it. Okay, something weird just happened. I think we have no spark once again. Yeah, no spark. I just reviewed the footage that I just recorded. And this thing, it tried to start almost immediately while it still had spark. Look at that, just a few rotations and boom, combustion. It wants to start, it's ready, it's pali napo ključac. No. The problem is that I destroyed this almost immediately. It died, this was left without spark, and of course without spark it will never start. But I figured out why I destroyed these. It's my battery. It's my battery. This is not designed to run with this. This is too much current, too much volts, too much you name it. My battery is literally frying these things, but of course I had to learn that after I destroyed 3 of them. But I ordered new ones, but I can't wait. I can't wait a few days for them to arrive. I have to do something today. And there is something that I did come up with. There's something I can do today. I'm gonna go now to the nearest auto parts store. I'm gonna buy some stuff, and I think I can give it another shot today. Okay, take 2. I'm not actually using the ignition thing that I just built. It's kind of difficult at time, kind of weird. The spark isn't as strong as I expected. Fortunately, I found somebody selling the same stuff from Amazon locally through OLX, if you're familiar with it. Went there, bought 4, of course, at a markup. Hooked it up again. Let's try again. I'm just doing this now to see what's gonna happen. Sometimes it does 2 quick pops, like pop, pop, pop. I think that's what we need. It needs to keep, I think it's just firing on one of the chambers. But this is fun too. Okay, I felt some resistance there. Oh no. It was this. It was this. Holy crap. Whoa. I've made a flamethrower. Okay, so a lot of gas, flamethrower. Less gas, pop machine. I know, there's a market for this. Honda owners.
It is hot, really hot. And the acrylic, the front cover, it's bent here, completely deformed.
Okay, so this is massive progress and a very important milestone no matter how you look at it, because I went from a metal engine that did absolutely nothing to a 3D printed engine that partially melted and fell apart after just 2 combustion events, to a 3D printed engine that did hundreds upon hundreds of combustions. I haven't showed all of them in the video. I tested more off video. I did hundreds, and this engine, it can do combustion at will, obviously. Also, it sometimes thinks it's a flamethrower, but we're gonna figure that out. And most importantly, it can survive all of these combustion events without melting or falling apart. Also, I have managed to get this engine to do little pops, little combustions with the gas turned off. So using just residual gas in the hose and turning the engine with some pliers, I got little pops, I got combustion events. Which proves that this engine is capable of generating vacuum, pulling in the air-fuel mixture, and then transferring it to the combustion area, and of course igniting it. And also I have checked out all the high-speed footage, and what's really impressive and what makes me really happy is that the seals are keeping the combustion contained. It's not going past the seals. Of course, I hoped the engine would start and run self-sustained for at least a second or two or something. I always hope, I always imagine it starting whenever I plan to do this and whenever I actually do it. But obviously it is very hard to get a novel, untested, unexplored engine anatomy to actually run on its own. Right now, I'm not sure why it didn't start. I have a few ideas, but I have to verify all of them to be sure. One of the things that comes to mind first is that I positioned the exhaust too close to the spark and vice versa. So the combustion may be going right out the exhaust before it actually has time to act on the rotor, to force it down, to create torque, and to keep creating torque. But there's a reason why the exhaust is here so high up, so close to the spark. But that's something I will cover in the next video, where I plan to do an in-depth analysis of this engine, of its anatomy, and to show and explain all the details and the tricks and the stuff I did to get it to this stage. Obviously, none of this would be possible without my Bambulab H2D, which is capable of printing these very, very impressive materials, and it's also capable of achieving very tight tolerances 100% consistently. I'm genuinely thankful that I live in a time where it's possible to do projects like this on a DIY level. A capable 3D printer is an incredibly cost-effective but also a time-saving approach. And that's because I have gone through, let's just move that over here. I have gone through dozens upon dozens of different seal dimensions, different caps, different chambers, different designs, rotors, you name it. I've gone through all of it. This is just a part of it. There's more there at the back of the room. What I'm trying to say is that outsourcing this would not only be terribly expensive, but actually having somebody make it for you and then ship every version to you so that you could test it and then tweak it and do your trial and error, it would take forever. If you have a 3D printer, you do it yourself without waiting for anybody. Also, I want to thank all of you for all of your valuable input and feedback and comments after the last video. I'm very new to 3D printing, and honestly, without your comments, I wouldn't know that you can 3D print TPU, for example. Actually, you can print it, but it's not that easy, because here's 3D printed TPU without drying, and here it is with drying. As you can see, the difference is massive. Turns out you need to dry the filament before printing. I didn't know that. But fortunately, one of my viewers sent me a very nice email where he taught me a lot and also told me about the AMS HT being high temperature. This is the secret sauce in my recipe. It's fully integrated into the Bambulab ecosystem. It's an automatic dryer. You plug it into the printer, you load the filament, you choose the filament, it automatically selects the temperature and the required drying time, and it even rotates the filament while drying to achieve perfectly consistent results. And finally, I'd like to thank whoever posted this video 15 years ago. As you can see, this is the design that my current engine is based on. It's just that this one is horizontal and mine's upright, but it's very nearly the same thing. Now, what happened is that when I found out that you can 3D print TPU, I immediately went back to the rotary vane engine because I thought, oh, I can finally seal it, I can get it to work. Well, it turns out that it's not the case. It was a massive failure. I wasted 2 weeks on this, designing it completely again from scratch, printing it. In the end, massive failure, but I learned a lot of lessons, and this is the failure that made today's milestone possible. By the way, that entire episode is going to be a members-only video, probably next week. I'll show you what happened with this. In general, there's going to be more members-only content because I really enjoy the ability to make different, weird, experimental, but also valuable content that isn't necessarily algorithm-friendly. Stuff like, I don't know, imagine a blog from 10 to 15 years ago, but in video. That's sort of what I'm trying to do with the members' content and building out a community, and we're all having fun along the way. So if you want to support the channel and want to see the content and more, consider becoming a member. So I went back to the rotary, I failed, and then I realized just how good my traveling chamber design actually was, because it solves all the problems of the rotary vane. And so I decided to pursue that path instead. And I went back to the drawing board and doing more research, and then eventually I stumbled upon this video. It is entirely in Russian. All the comments are in Russian, but I did eventually manage to connect this name, which is shown at the beginning of this video, to this name in this Russian patent, which shows a very similar but not an identical engine. But in any case, a video is worth a million pages of obfuscate patent language. So what I did is that I ripped out my favorite CAD software and decided to rip off this design. Speaking of CAD, I have been working intensely in Onshape over the past month, pretty much a few hours every day. And this engine and my rotary vane, they have been designed from scratch, from the ground up, entirely in Onshape. And as somebody who is self-taught in CAD, I have to say that I really appreciate and enjoy the software, its logic, it's overall just lovely. Also, because it's entirely cloud-based, you can run it anywhere, on any device, at any time, with zero pre-installed things and zero fancy hardware, because it runs in your browser while having all the capabilities of SolidWorks and Fusion and you name it. And because it's in your browser, it means that there are no downloads, no installations of anything ever, no updates, no crashes or lost work ever. If you want to try it for free for 6 months, there's a link below. And now, as I promised, why is this called an oval engine? But this one is called an elliptical engine, the old one. That's because this, the housing, is an ellipse in this one, and this one is an oval. But don't they look the same? Yes, they look almost the same, but mathematically, they are very different. An ellipse is a shape defined by two lines, the major and the minor axis. That's it. An oval can be any closed round shape. It can look like an egg or an oval or a track or whatever. There's many kinds of ovals. So all ellipses are ovals, but not all ovals are ellipses. This engine has an artificial shape. I created it by extending lines from the middle and then creating a spline around the ends of those lines. This creates a more rounded, a smoother, a easier travel path, an easier transition for the seals, which ultimately reduces friction and makes the engine easier to turn. This is something that I implemented already in my rotary vane before I even saw this design. But sure enough, when I traced the design from the video, it too is an oval and not an ellipse. It's just one of the many details hidden inside this engine, which I will show and talk about in the next video. Until then, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.